Okay, this is the beginning of day 3 for Unit 11, electrochemical cells under non-standard conditions. Standard conditions is 298 Kelvin or 25 degrees Celsius, and we assume that the solutions are 1 molar for both your cathode and the anode. But conditions are not always standard, as we know. Sometimes the temperature is different, sometimes the concentrations are different, and they're even different as the reaction progresses. Our Nernst equation, which is also available in the reference packet, we'll look at that in a minute, is that the standard potential, or the potential, is equal to the standard potential, which means, again, at standard conditions, that's what that degree symbol means, minus the gas constant times the Kelvin temperature divided by the number of moles of electrons that are being transferred, multiplied what's called the Faraday constant. That's also in your reference packet. And then also that whole proportion is multiplied by the natural log of Q. Faraday constant here is very long. You probably don't need that many significant figures when you do your calculations. Faraday constant in the packet has less. Again, for your calculations, use what you've got available to you. A Faraday, 1 Faraday, is the quantity of electric charge carried by 1 mole of electrons. Just like all other types of reactions, oxidation and reduction reactions occur in mole ratios. So when electrons are being transferred, we quantify that in moles, just like we do with other reactions. Q, or the reaction quotient, is just like the old Q that we have calculated in the past. Just like K, it's a reaction quotient, but it's not K in that we don't know for certain that we're at equilibrium yet, or we know we're not at equilibrium. Either way, either we don't know for certain, or we know we definitely are not. But we still calculate it the same way, but we can't call it K. We have to call it Q. If the temperature is still at 298, there's some shortcuts to that Nernst equation, which there's 2 versions of it here, in both natural log and also in base 10. Natural log you'll see in your book. That equation is provided in your book. The log base 10 equation is available in the reference packet. So that's why we decided to show you both of them. They'll both work. They're only mathematically a little bit different because mathematically natural log and log base 10, of course, are different. Since the reference packet is what you'll have available to you, that's what you'll probably want to use most often, but just FYI, it is also available in natural log. And interestingly enough, free energy, or Gibbs free energy, or delta G, also has a mathematical relationship with our standard voltage. As you can read there, it's negative or minus or opposite, again, the number of moles of electrons transferred times that Faraday constant, again, times the standard potential of the cell. And if you put in log of K instead of Q, if you know you're at equilibrium, you can then calculate the log. You can actually find your K value based off of your voltage, your potential difference. So just like any other type of equation, it could work both ways. You can calculate your voltage, or you can calculate your equilibrium constant, K. And we'll get some practice in doing some of these skills. There's the equation rearranged for natural log of K. Again, if you want to use this, that is the equation that is provided in the reference packet, or the base 10 one is. And that pretty much ends our notes for today. There is no more. The other attachment will be a little guidance on doing some classwork for the day. You were given a handout for Unit 11 Day 3 examples, so just simply click on the other video and you can watch me work through the class examples with you if you think you need that help. If you want to try the examples on your own first, you may, or you can watch me do one or all three of them, your choice.